Alright, thank you very much for having me here today. We are going to continue with chapter 9.1, which is on crude as a source of raw materials. So the last class we were discussing part 1 of crude as a source of raw materials. Today we are looking at part 2, which is the final part for chapter 9.1. And we have discussed on alkane, and we see alkane is an example of a hydrocarbon. It consists of only carbon and hydrogen, and it do not have any double bonds. It only consists of single bonds. If you still recall the formula of alkane, and I write on the right hand side, so there will be CnH2n plus 2. So I write it on the right hand side, just bear with me on this. So we know that the formula of alkane will be CnH2n plus 2, CnH2n plus 2. So what does it mean? It means that if the total number of carbon is 1, the total number of hydrogen will be 2 times 1 plus 2. Because the formula, once again, is CnH2n plus 2. So if you have 1 carbon, the total number of hydrogen will be 2 times 1 plus 2, which is 4. Alright, so CnH2n plus 2, so that will be, if it's 1 carbon, you will have 4 hydrogen within that particular compound. So what we are looking at for today here, we are going to look at a few examples and how do we draw the structure of these alkane compounds. So the first one here that we have is ethane. So once again, using the formula that we have CnH2n plus 2, CnH2n plus 2, we know that if it's ethane, and ethane consists of 2 carbons, the number of hydrogen will be 2 times 2 plus 2, which is 6. If you look at butane, if it's 4 carbon, number of hydrogen will be 2 times 4 plus 2, which is 10. So the point here is that if we look at ethane and we look at butane, what you will see is that once again, it consists of only single bonds if you look at the structural formula. So there's a few different diagrams that we can use here. We have structural formula, we have the condensed structural formula, and we have the electron dot diagram, which is known as the Lewis structure. It says here, structural formulas are similar to the valence structure. They show all the bonds in the molecule, but lone pairs can be omitted. So if you look at the structural formula, as you can see in this diagram towards the right hand side of the table, you can see ethane once again consists of 2 carbon and butane consists of 4 carbon. And when they are bonded to hydrogen, the bonds are only of single bonds. And you can see that no lone pair electrons are present. But in a way, if you look at ethane and butane, they do not really have any lone pair electrons because the carbon has 4 valence electrons, and each valence electron will be shared with the hydrogen atom. Eventually carbon will have 8 valence electrons, so all of them will be bonded to one and another. And hydrogen, it has 1 valence electron. If we share that 1 valence electron with carbon, eventually we have 2 valence electrons. So once again, when we talk about structural formula, it's very similar to a valence structure that we have discussed. It is not the same as the electron dot or Lewis structure. If you look at electron Lewis structure, you can see that it uses dots or crosses. As compared to structural formula, it uses the particle line, but in this particular case, structural formulas do not show the valence electrons. They are not bonded, which means that it does not show the lone pair electrons. If we look at the condensed structural formula, which is also known as a semi-structural formula, the reason why it's known as a semi-structural formula, because you can see that it does not show the line, it only shows the carbon and hydrogen. So let's just say if you have ethane, it will be CH3, CH3. Usually it shows in that particular form, so each carbon, how many hydrogen is bonded to each carbon. So it's breaking up the carbon one after another. So you can see that ethane has a condensed structural formula, or it's also known as the semi-structural formula. And ethane here will be CH3, CH3, butane will be CH3, CH2, CH2, CH3, or CH3, CH2 bracket 2, CH3. So if you look at ethane and butane, you can see the condensed structural formula, which is also known as a semi-structural formula, is different from the structural formula because it does not show the line. It only shows the carbon and hydrogen. So make sure you're very clear between the electron dot, which is known as the Lewis structure, as compared to the structure formula, which is very similar to the valence structure, but it does not show the lone pair electrons. And if you look at the condensed structure formula, it's known as the semi-structure formula. So make sure you know the difference between the three of them. And I'm going to move on to the next slide. So make sure you know, once again, when we talk about condensed structure formula, it's also known as the semi-structure formula, and it does not show the bonds. Move on to the next slide. Alright, so it says here represent three-dimensional molecules on a two-dimensional computer screen. Our page is a challenge for chemists. For example, each component of an alkane has 4 bonds in a tetrahedral arrangement. We know that when we are talking about a hydrocarbon, the most popular example that we have used in class was the covalent molecule, which is known as methane. And we know methane consists of 1 carbon and 4 hydrogen, CH4. So in this case, you see that it is of a tetrahedral arrangement. You see when the shape of the molecule is not important, it is often drawn in a simplified two-dimensional format. So usually that you will get a structure which is of a 3D shape, but it's very difficult for you to draw it. And let's just say that if the shape is not important, as compared to methane, the shape is very important to you to see the 3D structure, for you to know that it is of tetrahedral shape. But in this case, the other hydrocarbons that you see is not important in terms of that particular shape. As you can see here, a butane structure, for example, you will show it as a 2D structure, Alright, so I'm just going to move on to the next slide. So it says here, structural isomers of alkane. Structural isomers are molecules that have the same molecular formula but have different arrangement of atoms. The more atoms in the molecule, the more possible isomers there are. So today we're looking at something new here. We're talking about structural isomers. You need to know what is a structural isomers. When we're talking about structural isomers, they're the same molecular formula, but they have different arrangement of the atoms. So what does it mean? It means the structure will be different, but the molecular formula remains the same. So it says here, based on the second paragraph, the more atoms in the molecule, the more possible isomers there are. Alkanes that have 4 or more common atoms have more than one possible structure, which means that if you're talking about an alkane structure that has 3 or less carbon, you know that it does not have any structural formula. For example, if you look at methane, which has only 1 carbon, CH4 will always remain CH4. It cannot be anything else, so you can't have any structural formula. If you look at ethane, C2H8, no matter how you change the carbon, it still remains as the same structure, which is C2H6. The same goes for propane as well, C3H8, CnH2 and plus 2. Using the formula, CnH8 is the same scenario. Regardless of how you change the carbon, you know that the structure remains the same. So what this slide is trying to tell us is that structural formula is the change in the structure, which means that because of the different arrangement of the atoms, but the molecular formula remains the same. So there's something for you to know, which means that if that particular structure has 4 or more carbon atoms, it will have structural formula, structural isomers. That's what I mean, structural isomers. Move on to the next slide. So it says here, a CH3 side group is known as methyl group, as its structure is similar to that of methane with 1 less hydrogen. So if you look at this particular diagram here, you can see that there's A and there's B. A and B has the same molecular formula. They are both the same alkane. You can calculate the number common 1, 2, 3, 4 on A, 1, 2, 3, 4 on B. We know that both of them has the same molecular formula, which is C4H10. But what is different between them is that this is a structural isomer one to the other, which means that there's difference in terms of the arrangement of the atoms. For example, if you look at A here, this structure here do not have any branching. So if you look at structures like this, it's something that we will discuss more in class. If I look at B here, this is what we call a branch. So this is considered as a branch structure. So this is a branch. If you compare to A, and A do not have any branching. So A do not have any branching, but B has a branch. Alright, the point here is that if we are going to write the condensed structural formula, which is the one that does not show us the line, you can see that for A, the condensed structural formula will be CH3, CH2, and then there's 2 of them for CH2 and then CH3. If you look at B, that will be CH3, 3 of them, CH or CH3, CH, CH3. So how do we actually write the condensed structure formula? Once again, what you do is you look at one carbon and after another. So if you look at A here, the first carbon has three hydrogen. So the first carbon has 3 hydrogen in diagram A. So it will be CH3, and then with CH2 bracket 2 of them, and then CH3. If you look at B, it will be CH3, 3 of them, because there's 3 CH3, and then the center will be CH. So you write CH3 bracket 3 CH, or you can write CH3 CH CH3 bracket 2. Alright, so if you look at the structure, once again, A and B is showing you the same molecular formula, but there's difference in terms of the arrangement of the atoms. And diagram A and B, the one with the line, so the one with the line will be the structural formula. It does not show the lone pair electrons, but in this case, there's no lone pair electrons. And the green, the one that I highlighted in green, the dark green and the light green, that is the condensed structural formula for these particular diagrams. Bear in mind, they have the same molecular formula, but has changed is the arrangement of the atoms. Move on to the next slide. Alright, so this table here is from the textbook once again, so go through that. So what this is telling you is how do we name, and today we are going to talk about naming of the structural isomer, or a naming of alkane in this case. If I'm going to give you a particular alkane, what will be the name of that particular alkane? That's something for you to think about. So let's just say that in this case, you have a alkyl group with 1 to 5 carbons. If the alkyl group has 1 carbon, it will be CH3, is known as methyl. If it's 2 carbon, it's known as ethyl. If it's 3 carbon, it's known as propyl. If it's 4 carbon, it's known as butyl. If it's 5 carbon, it's known as pentyl. When do we use this alkyl group? Alkyl group is used when there's branching. Let's say there's branching that's connected to the main group, and I will be talking about what does the main group mean and what does the side group means, or the branch group means. So if you have a side group that is attached to a main group, the side group, you need to use the alkyl group. So the name has to be in alkyl. So methyl, ethyl, propyl, butyl, pentyl. And the main group will be ends with A and E. So that is the general idea on how do we name alkanes. Move on to the next slide. Alright, so here is on the condensed structure formula. So how do we write the condensed structure formula of a branch alkane? Once again, the diagram that we have at the top, this is a structural formula, and the one at the bottom is a condensed structural formula. And what you can see is that both of these is telling us that there is a branch. There is a branch on the third carbon. If you do your calculation on left or right, you know there's a branch on the third carbon. So today we're going to name that. And how do we name that? That's something for us to think about. So when you are naming that particular branch or the side chain, in this case, the third carbon, if you see the one at the top, on top of the third carbon, the carbon on top of the third carbon, that will be a side chain. And today we'll be talking about how do we name that particular third, carbon that's connected to your third carbon. So mostly you need to use the word alkyl group in order for you to name that particular structure. So in this case, the condensed structure formula will be CH3, CH2, CH, CH3 bracket CH2 CH3. So that is the condensed structure formula in orange, and the one that has second in red will be your structural formula. So make sure you know the difference between the structural formula and the condensed structure formula, in this case of a branch alkane. Moving on to the next slide. Alright, so if you look at this particular slide, it tells you about the melting and boiling point of the structural isomers of hexane. Hexane, based on what we discussed, has 6 carbons. So if you have hexane, you have 3-methylpentane. If you have 2-methylpentane, you have 2,3-dimethylbutane. We have 2,2-dimethylbutane. Once again, I will be guiding you through on how do we name this. But the general idea is that if it does not have any branching, you name it as hexane. If you have branching, then you have to name the location or the position of the branch, followed by how many carbons are there in the branch. If the branch has 1 carbon, it will be methyl. So you use methyl for your branching. If it's 1 carbon as a branch, it will be methyl. If it's 2 carbon, it will be ethyl. If it's 3 carbon, it will be propyl. If it's 4 carbon, it will be butyl, and so on. And we know that there will be changes in terms of the melting and boiling points. What does it mean here? You can see that if that particular alkene structure does not have any branching, if it does not have any branching, you can see that the melting point is actually very high, which means that if branching occurs in a way that it will make it more compact, which means it reduces its surface area of one alkane and another, and because of that, it will actually reduce the melting and the boiling point of the structure. So you can see that, look at hexane, for example. Hexane actually has the highest melting and boiling point as compared to the other structures. If you look at other structures like 3-methyl-pentene, its melting point and boiling points are lower. 2-methyl-pentene, melting and boiling points are lower than hexane once again. 2,3-dimethylbutane, the melting and boiling point is lower than hexane, and if you have 2,2-dimethylbutane, the melting and boiling point will also be lower than the one that we have for hexane. So the general idea is that if there is branching that occur, the more branching that occur, the lower the melting and boiling point, because that structure becomes more compact. So you can try and figure out in terms of the surface area of its contact with another hexane structure or another structure that consists of 6 carbon. We know that if it has branching, its surface area will be a lot smaller, which means its melting and boiling point will drop as a result. Moving on to the next slide. Alright, so now we are talking about how do we name our alkane. This is very important. Alright, so if you come across, let's say, exam questions that ask you to name based on the IUPAC, it's basically the naming system that we're going to use. So it's based on the International Union of Pure and Applied Chemistry system. It says the name of compound provides details of its structure. The following rules apply when naming alkanes. Number 1, identify the longest unbranched carbon chain. Number 2, number the carbon atoms in the chain from the end of the chain that will give the smallest numbers to branching groups. Number 3, name the alkyl groups after the alkane from which they are derived. Number 4, place the number and position of each alkyl group at the beginning of the compound's name. Number 5, if two identical side chains are present, use di as a prefix. For 3, use tri. If they are alkyl side chains of different lengths of the molecule, list them in alphabetical order at the start of the name with their numbers to indicate their respective positions. So, few steps here, not too difficult. Number 1, you have to find the longest unbranched carbon chain. So, this is point number 1. Number 2, you need to number the carbon atoms in the chain from end of the chain that will give the smallest number of branching groups. Number 3, name the alkyl groups after the alkane from which they are derived. So you have to find the branch and then you have to name it based on this alkyl group. Number 4, place the number and position of each alkyl group at the beginning of the compound's name. Number 5, if you have one side chain, then you don't need to have any prefix. If it's 2, it will be di. If it's 3, it will be tri. Number 6, if there are alkyl side chains of different lengths of molecule, list in alphabetical order at the start of the name. With the numbers indicate the respective position. So let's just look at a few examples for us to be very clear on how do we name alkanes. So let's just say we look at this example here. So it's asking you to use the IUPAC. So there's a system that we use to name the structural isomers, in this case of hexane. You know that it consists of 6 carbon. Hexane consists of 6 carbon, 1, 2, 3, 4, 5, 6 carbon. So step 1 is to identify the longest unbranched carbon chain. In this case, there's 5 carbon. So the one at the bottom here is actually your side chain, and that cannot be part of the naming of that particular main structure. So number 2, number the carbon starting from the end closest to the branch. So you have 5 carbon. Number 3, name the side branches and the main chain. So name the side branches and the main chain. So you have 5 carbon and you have that one side chain which is the methyl. It's known as methyl. HIL. You use that because there's only 1 carbon on that particular branch. So when you combine all that, make sure you do not leave any gaps. There is no gap. Do not leave a gap between the name itself. The whole thing has to be as one word. So you know that if you combine all the compounds together, you get 2-methylpentene. 2-methylpentene. Because when you are naming the carbon that is connected to the side chain, it must be the closest carbon to the end. Either on the end of the chain on the left or end of the chain on the right, it must be closest towards the end. So do not name this as 4-methyl pentane. This is not 4-methyl pentane because it begins, or the side chain is found on the second carbon of the pentane structure. So the naming here will be 2-methyl pentane as a result. Moving on to the next slide. Alright, so we are almost there. This slide here is telling you about the IUPAC systematic naming of 3 alkanes. So the first one will be 3-methyl pentane. You can see that the third carbon consists of the methyl, so it will be 3-methyl pentane. If you look at the second diagram, it will be 3,3-dimethyl pentane because the third carbon has 2 methyl group. And the third diagram here will be 2,3-dimethyl butane because it's on the second and third carbon. You look at this, the main chain will be consists of 4 carbon. Regardless of how you move around the structure, it consists of 4 carbon on the main chain, and then it has a methyl on the second carbon and a methyl on the third carbon. Alright, move on to the next slide. So we are really almost there as mentioned before. If you look at this one here, it says write the systematic names of the following molecule. So the main structure consists of 1, 2, 3, 4, 5, 6 carbon, and you can see the third carbon contains the methyl group. So in this case, the naming here and the side chain as mentioned consists of a methyl group. So the naming of the molecule will be 3-methylhexane. 3-methylhexane because it's the third carbon from one end or another, as mentioned before. It can be on the end on the left or on the right. If I go through this, the closest is actually towards the right. So in this case, we know that it's on the third carbon from the right hand side. So the name here must be 3-methylhexane. Do not leave a gap between methyl and hexane. That is unacceptable. So 3-methylhexane is your name for this particular structure. So let's look at this particular example here at the bottom alkane. I'll give you some hint here while you're working on this, and then we discuss this more in class. It consists of 5 carbon in the main chain. It has 1 methyl group on the third carbon as the side chain. So your main chain here, 5 carbon. So we go through that particular discussion before. If it's 5 carbon, this will be pentane, like a pentagon. So 5 carbon will be pentane, and we know that we have this side chain on the third carbon, and it's on the third carbon and consists of 1 methyl group. So most likely your answer will have to be maybe 3-methyl pentane. Think about it, whether you agree with me or not, and then we will discuss this more in class. Make sure you leave it as one word. Do not leave any gap between your name or between that particular name of the molecule. I'll discuss this more with you in class, and then do make sure you complete the questions as stated on school boards. If you have any questions, you're very welcome to post it on social media. I'll answer all questions, and then you can email me as well and I'll answer your questions. So I'll see you then.